Hi there, my name is Sadia Main Siddiqui and today's topic of discussion is quantum numbers. Before going to quantum numbers, let us discuss about the structure of an atom. Consider the neon atom. It is 2,8. The electronic configuration is 2,8. Like any other atom, neon has protons and neutrons in the center of the atom and electrons revolving around it. What is electronic configuration of neon? As we discussed earlier, it is 2,8. But what do you mean by electronic configuration? The electronic configuration determines the arrangement of electrons in the shells or orbits. As we know all these, let us come to quantum numbers. Quantum numbers determine the position of an electron in the orbitals. You must be wondering, what are these orbitals exactly? Let me make you understand this with a simple example. Let us consider that you went to a coffee shop and you saw a lighted banner there, be it a Coca-Cola banner or anything else. So, we know that lighted banner has neon gas present inside it to illuminate it. So, as it consists of neon gas, when we zoom inside it, we see the atom of neon gas. Further zooming gives us orbits or shells. Zooming further in, we see the suborbits, and further zooming gives us the orbitals. When we further zoom, we see that these electrons which are seen in the atom are actually embedded inside the orbitals. Electrons are probably denoted by E small minus. As we talked about orbitals, orbitals are of four types. They are the s orbital, the p orbital, the d orbital, and the f orbital. Considering the maximum number of electrons, we see that s orbital has 2 electrons at max, p 6 electrons at max, d 10 electrons at max, and f 14 electrons at max. Now, when we try to arrange these electrons inside the orbitals, we see that they do not come lonely. They feel that they should be packed inside boxes. So we consider the s orbital and pack 2 electrons inside each box. The p orbital, we pack it inside 6 electrons. Again, we pack the 10 electrons inside the d orbital. And lastly, we try to pack the 14 electrons inside the f orbital, which we will not probably discuss in this video. Let me tell you one important fact, that we need to fill the empty spaces first, and then we must go on to pair the electrons. Each arrowhead represents a single electron. Now, considering the quantum numbers, we know that quantum numbers are of 4 types. They are the principal, azimuthal, magnetic, and spin quantum numbers. Let us consider the principal quantum number. It is denoted by small n. Principal quantum numbers tell us about the shell number. Let us take a sample atom and let us say that it has 3 shells, namely the 1, 2, and 3 shells. What do we name them as? Yes, we name them as K, L, M, N, and so on. Now, when we consider about principal quantum numbers, we know that n is equals to 1, 2, 3, 4, and so on. And it represents K, L, M, N respectively. So what do you know about it? 1, 2, 3, 4 are actually natural numbers, and they are named so because they represent the shell number. Now, coming to azimuthal quantum number, which is denoted by small l, we know that small l is equals to 0, 1, 2, 3, and 4, so on. They actually are named so because to avoid the coinciding of the numbers, quantum numbers. The values of L are on the whole numbers. And eventually, these values of azimuthal quantum numbers represent the orbitals. Coming to the magnetic quantum numbers. Magnetic quantum numbers are represented as M and small subscript l. Let me tell you why it is resembled so. Because the magnetic quantum numbers are directly dependent on the azimuthal quantum numbers. Let's see it here. L is equal to 0, s orbital, m is equal to 0 and it has one value. L is equal to 1, p orbital, m is equal to -1, 0 or +1 and it has three values. L is equal to 2, d orbital, m is equal to -2, -1, 0, +1 and +2 and it has five values. And the subsequent values of electrons are given on the left hand side. So generally speaking, we can say that the value of magnetic quantum number is equals to -L up till +L. Coming to the spin quantum numbers. Spin quantum numbers are represented by a small s. S value can take up as +½ or -½ The value of the spin quantum numbers basically depends on the valence shell electrons. That means if the valence shell electrons is upright or it is pointing upwards, then the value of the spin quantum numbers will be +½ and if it is pointing downwards, then the value would be -½ Let us take an example to understand this furthermore. Consider the silicon atom which has 14 electrons inside it. The electronic configuration is 1s2, 2s2, 2p6, 3s2, 3p2. Now let's say that you have been given a question. Find out all the quantum numbers of the 3p2 electron inside the silicon atom. Now 3p2 has three parts, the 3, p and 2. The 3 actually resembles the shell number. That means it clearly says that the value of n is equal to 3 as the value of n is actually the shell number. Now coming to the p value, L is dependent on the p orbital. For p orbital, we know that the value of L is 1. Therefore, L is equals to 1. Now as I already told you, the magnetic quantum numbers is actually dependent on the L value. So as L is equals to 1, magnetic quantum number value should be -L to +L. So it must be -1, 0 and +1. Coming to the spin quantum numbers, as it is a p orbital, the three boxes are present as I told you earlier. But the 2 power which is shown on the p, it is denoting the number of electrons. So we probably fill the 2 electrons inside the 3 boxes, and as I told you, it must be filled in the 2 empty boxes first. What is the valence electron here? Yes, it is the second electron. So, as the valence electron is pointing upwards, the value of S is +½ Thus, the position of the 3p2 electron of silicon is determined. Thank you for watching.